In Unit 10, we're going to expand on what we did in Unit 9. We learned the basics of integration in Unit 9, integration being the area under the curve, and now we're going to expand on some more strategies for doing integration and also a couple more uses for integration. So this is our next big concept. We're going to separate our first order differential equations. So they give us this equation, dy dx, so a derivative, equals two different functions. So dy dx equals mx over ny. And you can see that the functions, the numerator in this case, one function is with respect to x and the other function is with respect to y. So we always do the same thing in this case. We separate and integrate, always. So our first step is going to be to cross multiply. So we multiply ny times dy, so we get ny dy, and then we multiply mx times dx, and we get mx dx. And what that means is now I have everything with the same variable on one side. So all my x's are on the right, and all my y's are on the left. And once they're all on one side, now I can integrate each side in order to find my next answer. So I would integrate this side, and I'll integrate it with respect with dy. So I'm integrating with respect to y, and this side I integrate with dx or respect to x. This is the general solution. Let's do an example, and I think this will make a little bit more sense. But separate and integrate, always my first order of what I do. Whenever I have this type, my first action is separate and integrate. Okay, so let's take an example. So first we're going to find the general solution for dy over dx equals 3xy squared. So first thing we're going to do is separate. So I'll divide this side by y squared, and I multiply by dx. So after I separate, my first step is always separate. And remember, it's important that I separate and I put all my y's on one side and all my x's on the other. My next step is going to be to integrate. So I add 1 to my exponent, I get -1, and I multiply by -1 as well. And then I do the power rule again for this, so it's 3 over 2 x squared plus c. Now, you are correct if you're thinking, why do I only have a plus c on the right side? Well, there is a constant on the left and there is a constant on the right. But when we combine them together, we just get one constant. And we always keep that constant with the x for simplicity's sake, because our equations are usually just y on the left. So it's not wrong if you put just the constant on the y side, but for simplicity's sake, we're always going to put it on the x side. And in the end, when you combine your constants together, there's always only one constant. So let's just rewrite this so it looks a little bit nicer. -1 over y is 3 over 2 x squared plus c. And now the next thing I'm going to do is find the particular solution. So what that means to find the particular solution, it means I'm going to plug in y as 2 and x as 1 and solve for c. Just like when I'm doing a linear equation of y equals mx plus b, and then I plug in my equation for x and y, and I solve for b. Same exact idea, but this time I have two variables, and I'm solving for c. So -1/2 is 3 over 2 times 1 squared plus c. So -1/2 is 3 over 2 plus c. I'll subtract, and I get -4/2 equals c, so c is -2. And again, I'm not done, because I have to plug in what the c is. Just like when we're writing the equation of a line, we always have to plug the b back in to find the specific solution. So -1 over y, 3 over 2 x squared minus 2. Now, this could be the answer, or it could be written as y equals. So it's really important that you have no problem rewriting it in any order. We could multiply through by y. There's lots of different things we could do. So you just have to be really flexible in how you see the answers for these. Now, while separate and integrate is definitely the next level up, these slope fields are no big deal at all. I don't really know why they throw them into this section, as they deal with derivatives, not antiderivatives. But again, these are not a big deal. And they're very often an open response problem. So when you see these as an open response problem, hopefully you take a big deep breath and a sigh of relief, because they're not that bad to deal with. So let's see. This wants us to find the slope field that represents this. So what we're going to do is plug in lots of different numbers and figure out what my derivative looks like. And then I'm going to graph it. So I always do my x's and my y's, and then my dy and my dx. So in this case, it does not matter what x is, because the derivative doesn't even have x in it at all. But it does have the y's in it. So let's see. We'll do negative 2, negative 1, 0, 1, and 2. And my x's, as I said, do not matter. They're always the same. So let's see. My derivative here is negative 2. My derivative is negative 1, 0, 1, and 2. And now we're going to draw our slope field. And the slope field always looks like this. It has little dots where it wants us to draw. So maybe you've seen this on an open response problem even if we haven't done it yet, but it always has these little dots where it wants us to draw our slopes. And those are just kind of guidelines to let us know where the slopes are supposed to go. Okay, this is a lot. Usually they don't ask us to draw this many points, and we're just going to do it for the first time. And let's see. I'll do it in red for this negative 2. So every time y is negative 2, we need a slope of negative 2. It doesn't have to be perfect, but I do want all of my negative 2's to look like the same. So let's see. If I'm going to say that that looks like a negative 2, then I want these to all look like negative 2's the same. They don't have to be a perfect negative 2, but we're going to be a good estimate. Now, negative 1 was going to be for this one. All of my negative 1's are negative 1's, no matter what the y value is. And my negative 1 should be a little bit less steep than my negative 2. So maybe like that. Maybe something like that. And then my zeros, let's do those in green. Those should be little flat lines. And then do my y's at positive 1 again. And I want them to look similar to my negative 1's, but going in the opposite direction. So again, not super, it's not really important, but what is important is that my 2's look more steep than my 1's. No one's going to grade you on perfectness of being able to draw a 2 for a slope, but I do need to know that it's more steep than a 1. And this is my slope field. These little tiny little lines, they're like abbreviated versions of what the slope would look like at that point. So what I mean by an abbreviated version is if it wasn't abbreviated, if it was the whole line, the whole tangent line through this point right here, it will be a nice long line going on indefinitely. But I only want a short window of that, so this right here is just giving me a short window of what I'm looking at. Now to draw my representation, what I'm going to do is to kind of connect the dots, see where this is going. Hopefully you can see that we would have something looking like this, and there would be lots of different solutions, and they would all kind of go up and go down like that. That's some representations of these. What's important to notice is there will always be like a rectangle around your box, and you just want to go make sure you go through the edges. You don't just want to connect any two. It's really important that you go all the way through the edges. So let's do that. It would look something like and again, it doesn't have to be perfect. You just want to show the general idea of what's going on. Now for this one, this is an example of how the slope fill would be asked as a multiple choice. And I just want to go through how I would do it. So the first thing I'm going to look at, I always look for my zeros because those are kind of the easier ones to look at. So here, whenever x is 0, it's looking like my derivative is also 0. So let's see which ones that could possibly be. Without effect on the y's, the only ones that let me know that the derivative could be 0 are a and c. No matter what the y value is, when I plug in 0, I'm going to get a 0 for my slope. So meaning that my slope does not depend on y at all. So now I know it's just in the variable of x. Now let's take a look at what happens. When x is positive, so I'm looking at these positive values over here. When x is positive, my slopes are positive. And here, when x is negative, my slopes are negative. So now I have to see which one of these would do that. When x is positive, my slope is positive, and when x is negative, my slope is negative. So it looks like the only one that does that is dy over dx equals x, because this would have flipped them. I would have had positives when my x's were negatives and negatives when my x's were positives. This might seem a little bit confusing, but I promise this is one of the most easy concepts we do, and once we start doing a couple of these problems, you won't have much difficulty.